Hi, welcome to the bonus lesson about conversion from hex to binary and vice versa. We are going to answer the question, why is every hex digit represented by 4 binary digits? Let's begin with a simple representation in base 16. We have this number. Every such A with an index like A0, A1, A2, A3 and so on represents one digit. So here we see that we can look at least 4 digits, and we have those points that mark that the number might be even longer. It might have some unknown number of digits. The value of this number is calculated like this: A0 times 16 to the 0 plus A1 times 16 to the first, and so on. As usual, just like we learned in previous lesson. We could, if we wanted, to represent each hex digit using 4 bits. Why could we do this? Because every hex digit is from 0 to 15. From 0 to F, I'll remind you. And 4 bits can actually represent all the numbers from 0 to 15. That is because 2 to the 4 is exactly 16. I recommend to look a few seconds at how it looks like. A0 is going to be represented as a binary number. This is a binary number, and we are looking here at 4 digits. Every such B with double index, this is B00, this is B10, and so on. This is one binary number with 4 bits, 4 binary digits. Also, the next one, A1, could be represented in a similar way. I remind you that those A0, A1, A2, and so on are the numbers from this equation. This is the same A0 as this one. And this is the same A1 as this A1. Those numbers, all those A0, A1, A2, and so on, are hex digits. So they could be numbers from 0 to 15. However, the B numbers are bits. They could only be 0 or 1. Again, we just rewrite it in some 2 different places of the screen, because we are going to look at some other stuff and we want to make sure that we can see it in the same time. In this part, we can see that we wrote part of the equation in new lines, so it could be easier to understand. If we take those new representations for A0, A1, A2, and A3, and so on, and we put them inside the original equation, that means we just take this A0 and replace it with this number, and take this number A1 and replace it with this number, and so on. We are going to get this equation, which is just like the above one, but we replaced A0, A1, A2, A3 in new representation, in base 2 representations. If we wanted, and in this case I do want to do it, I want to expand this representation in base 2 to the actual value. We are going to get this new formulation for the equation. We replace this number, this binary number, with its value. We know that these two are equal, so we are allowed to do this. And the same goes for the next one. This is actually, I remind you, this is just A0, but it looks different here. This is also just A0, this part. And the next one, this part, is A1. This is also A1. They just look a bit different because we represented them in the binary form. I remind you that those numbers, all those bits, are just bits. Now we can use again the fact that 2 to the 4 is 16, which is going to be useful here because we have all those 16 and we want to replace them with something related to base 2. And we are going to get this new equation. Everything we did is just replace every 16 with 2 to the 4. So we get here on the first power 0, and then 4, and then 8, and then 12. Eventually, if we open the braces, if we multiply, for example, 2 to the 4 with every element here, with every summand here, and we do the same with 2 to the 8 and 2 to the 12, it's not necessary to do it for the first part because this is just 2 to the 0 and it is just 1. We are going to get this new formulation. This new formulation is very interesting because now we can see some kind of sequence in the powers of 2. This is 2 to the 0, 1, 2, 3, and in the next row we already have 4, 5, 6, 7, 8, 9, 10, and so on. This is more like a binary representation of the number. We ended up with this formulation, this one here, and we are going to convert it to a binary number. We are going to do this as usual. This is just the usual value of a binary number, and we are going to go the opposite way and get back the original number. This is going to be the lowest digit because it is multiplied by 2 to the 0, and we put it here as the lowest one. Next, we go to this digit, B10, which is multiplied by 2 to the first. That means that it is going to be the second digit, and it is being put here. The next one is B20, and in the same way, we're going to put it here, the third one. And the fourth one is going to be B30, which is multiplied by 2 to the third. And we are going to put it here. And we go on with the next rows. We just put those bits together. We put the spaces here just to make it easier to look at, but we don't have to put them. Actually, this is a real binary number, and those are bits. All those B with indexes are just bits. They're just 0 or 1, each one of them. Eventually, we got this equation. The original number is written here, and on the other side we have groups of 4 bits, where every such 4 bits, if you remember, represent just one number. For example, those 4 bits, B00, B10, and so on, in the beginning they represented A0. We can go back just for a moment to see this. For example, we can see it here. A0 was originally B30, B20, B10, B00 in base 2. And here eventually, we get that at the total binary representation, those 4 bits are the last ones. The same we are going to get for A1, which is represented here by those 4 bits, B31, B21, and so on, and A3, which is represented by this quadruple, and A4, which is represented by this group. So we get that every hex digit is represented by exactly 4 bits.